Good morning. What we have this morning are several examples of very common collision-based problems. The very first of which is example 7.9 from the notes, and it's something called a ballistic pendulum. As it says, a ballistic pendulum is a device used to measure the speed of a projectile, such as a bullet. And the way it works is you fire this bullet into a hanging block, and that block, through conservation of momentum, starts to move, and it will move to a certain height based off of the speed of that block. From there, we can reverse engineer the speed of the bullet. So, to begin with, we have really three different stages. We have before the collision, which we'll mark as 1. We have immediately after the collision, before the block starts to move upward. And then finally, we have the block at its maximum height. So to start analyzing this situation, we're actually going to begin with our stage 1 to stage 2. And from this, we are just using conservation of momentum. So P1 is equal to P2. In this case, our initial momentum is going to be the mass of the bullet times, actually let's write mass B, times velocity 1 of the bullet. And our block, which we'll say is mass big M here, has an initial velocity of 0. So we'll get rid of that. We'll go ahead and just write that now. And that will be equal to both masses put together, because they stick together in an inelastic collision, times, we'll just say, V2. So, just from conservation of momentum, since we're looking for the speed of the projectile, which is V1b, we're going to go ahead and solve this for V1b. So since we've gotten rid of this term, V1b is simply going to be, I guess we should be a little more consistent here. So this is little m, and this one we can just say is V1. Let's leave it as V1 bullet. And so we have little m here, and so we're just going to take our mass big M plus little m times V2 and divide that by the mass of the bullet, little m. So this is from our conservation of momentum. The second part is we want to determine this as a function of the maximum height that the box goes to. So now we're going to look at 2 to 3. So from 2 to 3, we have a conservation of energy problem. And this is just like conservation of energy problems from the previous unit. So let's write our whole conservation of energy statement. And we're actually going to go from 2 to 3, so let's do K2 plus UG2 plus UE2 plus work equals K3 plus UG3 plus UE3. So, out of these, we can say that initially our height is 0, and it goes up to some other height, so our initial gravitational potential is 0. We have no mention of a spring or elastic stuff, so no elastic energy, and there's no friction that we can see here. At state 3, however, we're at a maximum height, so our speed goes to 0. So what we have left is K2 is equal to UG3. So replacing these, we have 1/2. Our mass is going to be the mass of the block and the bullet, so big M plus little m, times V2 squared, because this is at state 2. And then that's equal to mass, which is going to be big M plus little m still, times G times h, which is the height that this goes to. So, how do we go from here? Well, we're looking for V1b as a function of h. So what we can do is we can actually, if we want, replace V2 in this equation. So if we do that, let's see what we get. So I'm going to rearrange this again, and I would say V2 is equal to little m over big M plus little m times V1 of the bullet. And so now we're going to take this and we're going to substitute it into this equation. So what we end up with is 1/2, and actually we can go ahead and cancel out this m and m. So we have 1/2 times little m over big plus little m times V1b squared equals G times H. And now we need to square everything. So actually I'm going to go ahead and multiply both sides by 2 to get rid of this 1/2. And then what we have is something that we can square root. So I'm actually going to take this 1/2, get rid of it, and multiply by a 2 on the right-hand side. And then I have something I can just square root both sides. So then I can square root both sides, and I end up with m over big M plus little m times v1b, because I just square rooted something that's squared, equals the square root of 2gh. So now it's actually pretty easy to see that v1b, or v1, would be equal to m plus m over little m times the square root of 2gh. And there you go. So, having talked about the previous problem, we now also need to remind ourselves how to work with inelastic collisions. And these are pretty easy. The last one involved an inelastic collision. So just a quick reminder, we have in an inelastic collision, K1 is not equal to K2, but momentum 1 is equal to momentum 2. So for an inelastic collision, all we really have to go off of is conservation of momentum. So in this case, a quick reminder, and you're welcome to skip this if you remember how to do this kind of problem. We have initial momentum equals final momentum. And then we have ma times v1a plus mb times v1b equals mass A times v2a plus mass B times v2b. And in this case, we have no zero velocities that we know of. All we know is that after the collision, v2a and v2b must be the same because they are stuck together and moving. So we'll just call that v2. So what we now have is a situation where we can rewrite the right-hand side as simply mass A and mass B moving together as one big mass times v2. So if we find their common final x velocity, we have v2 is equal to the sum of the two momentums, mass A and mass B, initially, divided by the total mass once they stuck together. So substitution here will be 0.5 times positive 2. As you can see in our image, it is to the right. Don't forget these signs. Plus mass B, which is 0.3, times its initial velocity of negative 2, over the total mass, which is 0.5 plus 0.3. And so our final velocity ends up being positive 0.5 meters per second. So this is meant to be just a quick refresher of how to deal with an inelastic collision. Then, when you go on and talk about the initial and final kinetic energies, you can do so rather easily because K1 is going to be equal to Ka plus Kb, and I guess we'll say that these are K1a and K1b, which is 1/2 mass of A times its initial velocity squared plus 1/2 mass of B times its initial velocity squared. And so for this, we'll have 1/2 times 0.5 times positive 2 squared plus 1/2 times 0.3 times negative 2 squared. And it truthfully doesn't matter which is which. We end up with a final kinetic energy of 1.6 joules. Then, to talk about K2, we have simply the total mass, so mass A plus mass B, times their common velocity of 0.5 squared. So this is a lot easier to do. Oh, I guess I should have gone ahead and just said that this was 1/2 times 0.5 plus 0.3 times 0.5 squared. And so this final kinetic energy is only 0.1 joules. So you can see that quite a bit of kinetic energy is lost in this inelastic collision. And the reason that it's lost is that in order for these to stick together, there has to be some reshaping of the system so that they stick together. And that's where that energy goes. The final example that we need to cover before we have a quiz and before we do additional practice is a collision in 2 dimensions. All along in this unit, we have said that P1 is equal to P2 in any collision. But we've been neglecting the fact that momentum is a vector. So when we talk about conservation of momentum and P1 being equal to P2, we could additionally say that P1x is equal to P2x and P1y is equal to P2y. So these two are separate equations that equate to overall momentum being conserved. So when we go into a two-dimensional problem, we actually need to think about the fact that the x direction is separate from the y. So this is not too difficult and just involves a little bit of trigonometry. So we can start by writing, again, our conservation of momentum in the x direction. And so we can say ma, so here is our initial a, times v1a in the x direction plus mass b times v1b in the x direction, which is given to be 0 in this case, is equal to mass a times v2a now in the x direction plus mass b times v2b in the x direction. So this is 0, and we can actually see that in this case we have a little bit of an issue because we end up with two unknowns. So let's actually go a little bit further. So I'm going to go ahead and substitute some known values. So mass A we don't know, but we do know that it has the same mass as mass B. So over here I'm going to write a little statement. I'm going to say that mass A is equal to mass B and that they're both equal to some mass m. So if I rewrite this, I would have just mass m times v1a in the x, and then I can go on and say this is mass m times v2, and I'm actually going to go ahead and use trigonometry here. So this involves two components, and this right here is v2a in the x, and this would be v2a in the y. So I can say that v2a in the x would simply be v2, or as they said here, v prime, times the cosine of 45 degrees. And I'll do the same thing for b. So it's mass m again, and then it's v2, so this should be v2a, and this is v2b, times the cosine of 45 degrees. So let's do a simplification. We can get rid of all of these m's, and we come up with a simple statement of v1a, which we actually know what that is. The v1a is initially 3 meters per second. So let's just go ahead and plug that in. And that's equal to v2a times the cosine of 45 degrees plus v2b times the cosine of 45 degrees. So this is a little ugly, but if we want to, we can simplify this a little bit more. Let's go ahead and do that. I'm going to divide every single thing in this by cosine of 45 degrees. When I do that, what I end up with is 4.243 on the left, so that's 3 divided by cosine of 45, and that's equal to v2a and v2b. All right, so this right here is what we'll say is equation number 1 that we're working with. And so because this is an elastic collision, we can actually go a little bit further, but we don't need to do that right now because we haven't dealt with the y direction yet. So let's deal with the y direction. So P1y is equal to P2y. Let's separate these. So we can write this as ma times v1a y plus mass b times v1b y. And now both of those are 0. Neither of these are moving in the y direction to start, so that helps a bit. Is equal to mass a times v2a in the y plus mass b times v2b in the y. So let's make our simplifications. First off, neither of these have any y velocity initially, and so that makes the left side 0. And on the right-hand side, we have mass a, which we can just write as mass m, times v2a multiplied by the sine of 45 degrees, plus mass b, which is also m, times v2b times the sine of 45 degrees. All right, when you see this, you'll see now that mass cancels out, sine of 45 degrees cancels out, and what you end up with is simply that we'll write it this way first, 0 is equal to v2a plus v2b. Therefore, v2a is equal to the negative v2b. So we can take this and plug this in up here, since we have v2a and v2b. So what does that tell us? Well, it tells us, actually, it doesn't tell us what I want it to tell us, because truthfully I could not have done this step. So I apologize, but we made a mistake. I made a mistake, where I'm not dealing with sine of 45 in both. I'm actually dealing with sine of negative 45 for one of them. So in this case, we actually have a little bit of a difference. We actually end up with a case where we have v2a minus v2b is equal to 0. Therefore, v2a and v2b are the same. Now keep in mind this is just the magnitude. So that helps us a lot, because we can take this, what we'll say is our relationship number 2, and we can plug that back in to our equation number 1. So let's write this in a light blue. If v2a is equal to v2b, then we can say that that's equal to, let's just say v. Therefore, up here we would have 2v is equal to 4.243. Therefore, velocity, which is equal to v2a and v2b, these are the speeds of each, is going to be 4.243 divided by 2, which is 2.1, we'll just say 12. We'll round it a little. So this right here is our answer, and that is just the speeds that we're looking for. And the way that we did that is we separated the x and the y directions for our collision. You have to be careful, however, and it even gave me a hint, I just wasn't looking, that the angle in this case is a negative reference angle, because they are not actually identical angles. So you must be careful of that. Even I made that mistake. All right, so this is the last new thing before we have a quiz, and truthfully, it just ends up being a lot of systems of equations that you have to solve. And what I really would hope is that you intuitively have an understanding of how a two-dimensional collision works, such that initially we had 0 y motion, so the y momentum was 0. Therefore, at the end, after our collision, we must have a total y momentum of 0. So just like projectiles, you can split up collisions into x and y directions and treat each one separately. Just be careful of the angles.